tá certo? Só quero dizer para vocês que a aula magna, ela é o início, como o nosso vice-diretor vai dizer, e ela tem que ser motivacional, né? Ela tem que ser em temas que podem despertar o seu interesse. Nós, físicos, vivemos de motivação. Às vezes a gente tem uma motivação íntima muito grande, mas em 99% dos casos, a gente observando pessoas e a opinião delas, desenvolvemos as nossas motivações e as nossas paixões para levar a ciência adiante, né? Então, a mensagem de uma aula dessa vai muito além da física que vai ser apresentada. Claro que uma das coisas mais modernas é a parte quântica, né? Então ele vai dizer, numa linguagem bem coloquial, os conceitos, as coisas que estão mudando a nossa forma de enxergar o mundo quântico, mas vocês devem enxergar além, tá certo? É o que você pode tirar de mensagem, é o que você pode construir a motivação para essa carreira que nós escolhemos, né? Eu escolhi muito tempo atrás, alguns colegas daqui e agora vocês. E acredite, a gente é movido por aquilo que está dentro da gente. Nós temos que toda hora criar um monumento dentro e a gente vai então lapidando esse monumento. E a motivação é fundamental. Então é por isso que a gente fez o esforço de trazer um físico que é um expert em motivar as pessoas pelo número de pessoas que ele já colocou em física. Tá certo? Então a gente vai começar, peço desculpa, em nome da direção do Instituto, da tradução, mas essas coisas, como sempre, está totalmente fora do que a gente pode controlar. Eu vou chamar o professor Richard Garrett, que é o nosso vice-diretor, para dar início às atividades.
Obrigado, Vanderlei. Bom dia a todos. Meu nome é Richard, para quem não me conhece, que deve ser a grande maioria aqui, com certeza. Mas é muito bom ver o auditório tão cheio para, então, assistir à aula magna do ano acadêmico 2017. Como o Vanderlei falou um pouquinho agora há pouco sobre a importância da aula magna, basicamente representa o início das atividades acadêmicas do ano. E, por isso, a gente busca trazer sempre alguém que, de fato, vai motivar vocês, vai contagiar vocês com seu próprio entusiasmo pela ciência que desenvolve. E, evidentemente, esse ano não é uma exceção em relação a isso. É um grande prazer, é uma honra para nós recebermos de volta ao IFSC o professor Daniel Kleppner, do MIT, Massachusetts Institute of Technology, que já esteve aqui conosco uma meia dúzia de vezes ao longo dos últimos 30 anos. E eu tenho certeza que no final da palestra dele, vocês vão estar totalmente convencidos de que vocês tomaram a decisão certa de optar por física, vindo aqui, juntando-se a nós nesse empreendimento mundial, que é aquilo que cientistas fazem, que é desvendar os mistérios da natureza e do universo. Não tem nada melhor para você fazer ao longo das poucas décadas que cada um de nós tem na face do planeta. Com certeza, a palestra do professor Kleppner vai servir para convencer vocês que vocês estão no caminho certo. Mas agora eu vou mudar de língua e agradecer a presença do professor Kleppner em inglês. So, I always get a little bit nervous when I have to speak English, because people expect me to do it well. That is not always the case. Anyway, I would just like to spend a few words saying thank you once again to Professor Kleppner. I know you've had a tough journey to get here and only a few hours sleep last night. We really do appreciate your presence with us. We're absolutely certain that your talk will be a stimulating talk, which will motivate our students in there, and they will remember it probably for the rest of their careers. Actually, it's not just a question of welcoming Professor Kleppner to IFSC. I would say we're welcoming you back, because in a sense, you are one of us. Probably most of you don't know this, but Professor Kleppner is one of only 2 honorary professors of the Institute of Physics here in São Carlos. So in a sense, you're one of us, and we're welcoming you back home. Nobody more appropriate to give the Aula Magna, the inaugural lecture for 2017. Vanderlei, did you want to say something more about Professor Kleppner's scientific career before we actually finally allow him to say something?
Okay. Thank you, Richard. Richard is afraid to speak English. I am always in panic because I know that I'm going to do some mistakes. But I will just introduce you Professor Daniel Kleppner. And for me, it's hard to introduce Dan Kleppner because I've been speaking about him my whole life. He is a mentor. He was a mentor for me and for other people in Brazil. I think Brazilian students doing physics at MIT met Dan Kleppner and got the enthusiasm that he can pass to us. And so I've been speaking so long about Dan Kleppner that I don't know if I can now say in a compact way 5 minutes of his career. Dan Kleppner is an American. I think he did his high school in New York.
Near New York.
New York. And already in high school, he got some very important mentors that was telling him indirectly that his talent was physics. I don't know if you believe at that time that your talent was physics. It seems that you didn't know exactly in high school to take the decision. But some people in his life, in high school, were fundamental for him to take that decision. They give him the right motivation. And then he decided to study physics. And at that time, physics had a lot of different challenges. But he was motivated enough and moved to England for his bachelor. And got his bachelor degree. And doing his bachelor degree, he also met people that was mentor to him, that drive him to the right direction. And I learned from him that you hear about Norman Ramsey when you didn't know him yet. And you read his book about nuclear momentum.
Mm-hmm.
And then his professors in the undergraduate told him, oh, that's a field to go. It's called atomic physics. And then after finishing, he decided to do his PhD. And then is when he landed at Harvard University. And surprisingly, walking in the corridor, he finds the name of Norman Ramsey. And I said, this is the guy. And then he started to study his PhD with Norman Ramsey. That's Nobel Prize in 89 in physics. And one of the key persons for atomic clocks and hydrogen maser and everything. He did a thesis, and he basically invented the hydrogen maser that today is a very important device in all the telecommunication, navigation, and so on. After finishing his PhD, he decided to continue on this. And he was hired as assistant professor in Harvard first, and then a full professor at MIT. And at MIT, Dan Kleppner did work in fields that today are very fundamental for us to continue to understand the quantum nature of matter. So he started the field of, he was one of the pioneers at least, in Heidelberg atoms. Heidelberg atoms are atoms very high excited, that tell us a lot of things about how things are going on in between electrons very close to the nuclei and very far. And he studied, I think, the first time, the establishment of a chaotic type of effect in the levels of the quantum system. He also was the starting person for quantum atoms in cavity, quantum electrodynamics. And ended by Sérgio Mascarenhas taking that and getting Nobel Prize 2 years ago. And I think Sérgio Mascarenhas was working with you for a while, right? And Sérgio Mascarenhas came here 2 years ago too with you. But that's not enough. Then Kleppner also works in field of precision. You see, we don't, when we learn in school the fundamental constants, we learn, oh, velocity of light is now definition. Sometimes we forget how much science is behind the determination of fundamental constants. In fact, it's not to exaggerate to say that to determine the precision of nature is the main source of evolution of our knowledge in physics today. Trying to measure well things is what made physics evolve the way it has been done. And Dan is being one of the seminal person in this field, right? He's, I would say, one of the men behind the atomic clock. But that's not enough. He also worked in the beginning of the quantum gases. We all learn quantum mechanics, and we say, why we don't see that by eyes? In some situation, we do, which is many different effects. One of them is the called Bose-Einstein condensation. And then Kleppner was one of the brave scientists that say, I want to do Bose condensation in hydrogen. And he started to produce people. Some of the people he produced in his lab did the condensation before he did. Eddie Cornell, Wolfgang Ketterle, Andy Hewlett. Eddie Cornell and Andy Hewlett got Nobel Prize. And Carl Wyman was also in your lab and also got Nobel Prize. Dave Neweiland is also related to you through Norman Ramsey and also got Nobel Prize. So Dan has touched so important fields that today people appreciate so much that he got all the prizes that a physicist can get. I'm not going to read all the medals, but this year, 3 weeks ago, about a month ago, was in January, the APS, he got the most important prize in the United States, which is a prize they give for recognition of the overall work you have done in physics. So he's one of those recipients. He did not get Nobel Prize yet. But he tells us that doesn't matter. And really doesn't matter because he didn't get one Nobel Prize. He got 6. 6 of his students or people that passed to his lab or is related to him got Nobel Prize. I think Dan walked to the Nobel ceremony more than any Nobel Prize that we know. And of course, he is one of the legend of MIT in physics. He started many important fields. He worked with people that, if you see the names, there are people that even today we study the books. And so we thought it was a great idea to bring Dan to tell you a little bit about the history of all this and what still left behind for us to do, which is some of the things you have to learn. That is one important thing with Dan Kleppner. He believes that you have to have mentors. You have to watch people. You have to get example in science. And you know, Dan, you've been my example for many years and always accepting invitations and always receiving us, not only me, but many Brazilians that go to MIT. And we appreciate very much you here. And please, you have the time now to give your lecture. Thank you.
Okay. Yeah. All right. I will try to use this, but sometimes I get excited. Anyway, okay. What I wanted to say is that over these years, I've watched the university develop, and that's been a great pleasure, because now there is such wonderful physics being done here that it is always a joy to visit. I also enjoy visiting because people here are so friendly, and the food is so good that I always think of Brazil very warmly, and of this institution very warmly, and Vanderlei very warmly. He's an institution in himself. Vanderlei told you a little bit about my career and the importance of mentors, good teachers, and they've been very important to me. My high school teacher was Arthur B. Hussey. He taught me in my senior year. That's the first time I really encountered physics, and he was so inspiring. I left knowing that I wanted to be a physicist. That's very helpful if you know what you want to do at an early age. Along the way, I had sort of other ideas when I learned about other things, but it's always been physics. In my college, a little college in Massachusetts called Williams College, a liberal arts school, they had a very fine physics department, and the teachers there were very kind to me. I wanted to do a project on my own, and they gave me laboratory space and spent a lot of time explaining electronics to me. So I had a good deal of experimental experience as an undergraduate. Then I went to Cambridge University for 2 years as an undergraduate. And in my second year, I had a very wonderful young physicist, Kenneth Smith, who told me about the work that he was doing. And I think that's a good place to leap off into what I'm really going to talk about now. I'm going to talk, it's basically about my research. And this is kind of distorted because there are so many things have been going on during that period, so many wonderful advances. So I'm just talking about a few of them. And so many people collaborated with me and worked with me that I can't start to list them all. So please don't get the impression here that I'm the man who did everything. I'm the man who directed the students who did everything. Now, this field, which I've called quantum science, is basically the science which has emerged since the discovery of atom cooling and cavity QED. These first emerged about 30 years ago. They started to develop, and the field has exploded now. It is, well, the best example of that explosion was this award the American Physical Society gave me this year. This award was selected by representatives of all of the divisions of the American Physical Society. And what it does is to recognize that this field itself is now a forefront field and one of the most exciting fields in physics. Last year it was given for the first time in theory for the creation of string theory by Ed Witten. This year they gave it for the creation of what I'm calling quantum science here, for this body of work which has stimulated so many people and has caused such excitement. And I would like to show where some of that came from. Now, I know that most of you here are just starting out in physics, and you may be wondering how you ever get to where physics is really done. It seems so remote, so far away. How does one do physics? Well, I'll give you a few examples of how these ideas grew and how important it is to talk to others, to interact with others, and to keep your eyes open and to have the right combination of courage and foolishness. So, the first seed. By a seed, I mean some idea which has grown and propagated. And this is atomic clocks. And I want to go back to the beginning, since most of you do not know that much about modern physics. So it begins with a famous experiment done in 1922 by Otto Stern and Walter Gerlach at the University of Hamburg. Stern was pioneering a subject called molecular beams. This is physics you do by letting a stream of atoms go through a high vacuum so they can move without deflection. And what he was doing was studying the properties of atoms which had little magnetism to them. The electrons going around basically form a little magnet. And because of that magnet, if you put them in a magnetic field, the magnets, they try to align along the field, but because of their angular momentum, it's just like a gyroscope which precesses around. If you put it in a non-uniform field, they feel the force. And what he did was to take, there is the laser pointer, there's a yes. Yeah, thank you. No, I can do it easily. Yeah. No, it's okay. Here's a stream of atoms going through a high vacuum, and they're going through this magnet, but the magnet, as you notice, it has one sharp pole and one rounded pole, so the field is a very non-uniform field, and that causes a force on the atoms. So they start moving up or down, depending on how they are oriented with respect to the field. Now, according to the laws of classical physics, they can be oriented anyway. What Stern found is that the atoms which came out, which he measured, deposited on a screen, some got deflected up and others got deflected down. There were none in the middle. They weren't oriented anywhere. And in fact, this was proof of what's called space quantization. The angular momentum could either point up or point down. This was terribly important in propelling the creation of quantum mechanics at the time. An American who went there a few years later, I. Rabi, told me that people were just amazed. They were coming around for the first time. They had to take quantum ideas seriously. So this experiment launched the golden age of quantum mechanics, which followed very quickly with the works of Heisenberg and Schrödinger and others. Now, yes, there's Stern. He received the Nobel Prize in 1943. It's interesting, Einstein and Stern were friends, and Einstein took an interest in Stern's work and sort of advised and collaborated with him. Okay. Now, this young American physicist who was there, I. Rabi, returned to the United States and continued working with this deflection of molecular beams. He set up a laboratory at Columbia, and yes, there he is. He received the Nobel Prize in 1944. He was using this deflection method. This is a Stern-Gerlach magnet there and another one there, pointing in opposite directions and deflecting the atoms first one way and then another. What could you do with this? Well, by looking at these deflections, you could find out about the nuclear properties for the atoms. He was really interested in nuclear physics, and he was measuring what are called nuclear magnetic moments by looking at the deflections of atoms and fields. And then he got, in 1937, a fantastic idea. What he did, what he did was to put another magnet between the two deflecting magnets. It's called the C magnet. Oops. And in that C magnet, he put on a radio frequency field. Now, I told you that these atoms precess around the magnetic field just like little gyroscopes. Well, it turns out if you put on a rotating magnetic field, which precesses the same way, you can reorient the atoms. You can go from one state to another. And when you do that, you detect it because they don't come out the other end. If they change their state here, they'll be deflected one way there, but the wrong way over there, and they'll miss the detector. And that's the principle of microwave nuclear magnetic resonance. So this had fantastic consequences. What I've shown here is you may recognize it. It's a resonance curve. It's what happens when you take a harmonic oscillator and drive it. The width of that curve depends how long the atoms in the oscillating field, how long you spend to take the measurement. If you keep the atoms in an oscillating field very long time, it gets to be very, very narrow. If it's a short time, it's very broad. The frequency with which this occurs depends on the strength of the magnetic moment of the atom and the magnetic field. So using this method, you can start measuring magnetic moments with very great precision. And that is the basis of the atomic clock. In the atomic clock, you're not measuring the magnetic moment, but you are measuring a transition frequency in the atom, which reorients the electron. And this had a very interesting consequence just then. Robbie, conceived the idea that you could use this technique to make a very carefully tuned oscillator, which could be used as the basis of a clock. So here is an article by William Lawrence in the New York Times in 1946, Cosmic Pendulum for Clock Planned. It reports Robbie's proposal. This is an interesting proposal because this is the only written report on it. Robbie never published a paper on it. He just gave a speech. He didn't really like writing, which is a fault. But there was a very good reporter, and he reported that. And one of the things that's in the article, Professor Robbie said that he would like to see someone build an atomic clock that would be capable of providing, for the first time, a terrestrial check on Einstein's postulate that the gravitational field produces a change in the frequency of radiation. Well, Kenneth Smith was doing molecular beam magnetic resonance, told me about that. I met with him. We had the tutorial system at Cambridge, and he was my tutor. And I remember him telling me about that. And the idea seemed absolutely fascinating. That gravity could affect time seemed to me inconceivable. Well, it was inconceivable to me at the time, although now I can conceive of it because it's true. But I didn't do anything about it. I was still an undergraduate. Should we try that? All right, we'll try a better mic. Anyway, I remember that idea stuck in my head. After Cambridge, I went to Harvard University, and I met Norman Ramsey. And that was a very fortunate thing for me because he was a great physicist, a great mentor, turned out to be a lifelong friend. But I walked in at a good time because he just had a great idea. Let me go back a bit, though, because Ramsey invented this method called separated oscillatory fields. And this is the method which allowed Robbie's idea of an atomic clock to become a reality. I'll explain a little bit about what it means. What it means is, I said that the longer the atoms spend in that interacting with the radio frequency field, essentially the longer the time you're making the measurement, the sharper it would be. And Ramsey wanted to make a machine longer and longer and longer. The transitions he was looking at depended on the strength of the field. And one of the problems he had to encounter was that as you made the precision higher and higher, you had to keep the field more and more uniform, and that became a terrible problem. And then he realized that if the atoms are going through a long apparatus like that, where you're making the measurement, and if instead of having this oscillating field on the whole time, you just have it on here,